All right, this is the lesson video I've been kind of avoiding making because lesson 10 is kind of intense. All right, we're gonna challenge your brain thinking for a little bit here. All right, 10 brings in this idea of a new kind of number. So and it says we're going to invent a new number. We're not going to invent it. It's been invented. It's been around for a long time. But you might not know about it. So we're going to try to expand your brain to some place that you have probably not thought of before. So I love how they start us off here because they take us at 10.1 and they remind us that all numbers have had to be invented at some point in time. So let's read this situation and see what they're talking about. Jada was helping her cousin with his math homework. He was supposed to solve the equation 8 plus x equals 5. And he said, if I subtract 8 from both sides, I get x equals 5 minus 8. And this doesn't make sense. You can't subtract a bigger number from a smaller number. If I have 5 grapes, I can't eat 8 of them. So, what do you think Jada could say to her cousin to help him understand why 5 minus 8 actually can make sense? And you, sitting here in a high school class, probably think very little of doing something like 5 minus 8. You probably very quickly thought, well, it's just a negative 3. Because you know about negative numbers. And so it seems like Jada's cousin doesn't know that negative numbers exist. So if Jada's cousin doesn't know about negative numbers, he would say that this is impossible, that 5 minus 8, we can't take away a bigger number from a smaller number. And it's, if we could even probably guess what Jada's cousin's age is, he's probably somewhere around about maybe 3rd grade. I think in 3rd grade you started thinking about negative numbers. And your teacher probably had something like a number line up on the wall. And instead of just using counting numbers, 1, 2, 3, 4, and so on, by this point you probably realized that you could do things like half numbers. And so they had started introducing ideas like 1/2. And maybe at this point in your life, you had already seen something like 2.2, some decimals, or mixed fractions. And then somewhere around about 3rd grade, or a little earlier than that, your teacher extended the number line this way and said, well, we do also have negative numbers. And so we had to start learning how to use negatives. And then we could start doing things like being up here at 5 on the number line, which I guess would be right about here, and subtracting 8, which just means we're going to move this way 8 spaces, and we would arrive at negative 3. And eventually your brain said, okay, that makes sense. So they invented all of these different kinds of numbers because they needed them at different purposes in their lives. Very early man only needed to be able to count things. They needed to know how many children they had, how many bison they needed to kill to feed their families, how many fish they caught in the river. They could just count using whole numbers. And then people started saying, well, maybe I don't have whole numbers, maybe I have these things in the middle here. And so they started adding things like fractions and decimals. And then came our negative numbers, and negative numbers especially came in for things like debt and to owe somebody something. So as soon as we needed to start owing somebody, right, we could have a farmer that could give you 3 bushels of apples now, and then you would give them 4 chickens in trade when your chickens were ready to be slaughtered. I don't know why I'm talking about killing so many animals right now, but sorry. But it was that kind of thing. It was the barter system, right? If you can trade 3 bushels of asparagus at the beginning of the season in return for 4 bushels of apples at the end of the growing season, you owe somebody something. So they have to remember, well, I've got 10 bushels of apples, but I owe 4 of them already to someone, or you're in debt. Your bank account can go negative. Not very negative, because they don't let you go much below 0. But it just means that you're in debt. You owe somebody. So that's what originally brought up negative numbers and the need for that. And then they also realized that, okay, we can have negative fractions. And we've been dealing with negative fractional exponents this unit, so we're okay with negative fractions. And they also discovered some other stuff in here, like the square root of 2, which is an irrational number. That means it never stops, and it never stops going. It's a 1 with all kinds of different decimals after it. We found out things like pi. And so we have all of these amazing numbers. And then you also have wrapped your brain around some pre-algebra concepts. Things like we don't just have one number line going left and right. We also have another number line going up and down, and we call those x and y. And now we can start plotting things in 2 dimensions, and we can make these wonderful shapes. And then we can spin shapes around, and we can stretch them and make them larger, and shrink them and make them skinnier. And now we can make scale drawings of things. So your brain also understood this idea that we work in 2 dimensions. And we also have talked this unit about 3 dimensions, about cubics and things like that. So numbers are invented, and we invent them as we need them. And so the new kind of number that we are going to be inventing deals with the square root of -1. So real solutions, real numbers, can fit on this number line. And so the equation x squared equals 9 has 2 real solutions. Okay, we can see this on the graph of y equals x squared. We can go through that, and we can draw points on this real number line to represent. So if we said, well, x squared equals 9, we're going to do the square root of both sides. And remember, we started somewhere that if we had a squared, that if we start with a squared, we're going to have 2 answers. We have to find 2. It's a law. It's in fact called the fundamental theorem of algebra, that if we have something squared, whatever is the highest degree of a polynomial, we have that many solutions. Okay, so we found out that we could have positive or negative square root of 9. Square root of 9 is 3, so we could have positive or negative 3. That means we could plot this at positive 3 or at negative 3. Because negative 3 times negative 3 is positive 9. Positive 3 times positive 3 is positive 9. We're good to go. So that would represent those 2 solutions. How many real solutions does x squared minus 0 have? Well, square root both sides. We said x squared has to have 2 solutions, so it's the positive and negative square root of 0. The square root of 0 is 0, and it's positive or negative 0. But 0 doesn't really have a positive and a negative. So this is when they came up with the idea of needing a word back from Unit 2, multiplicities. So x could equal 0 with a multiplicity of 2. You remember that multiplicity thing? It's when we were saying, oh, look, this thing happens twice. It bounces right there on the x-axis, right? And so we would say things like, oh, well, this would be x plus 3, and we'd throw a 2 up there as the exponent had a multiplicity. Okay, so that one happened twice, right on top of each other at -3. This one happens twice, right on top of each other at 0. So we can put that on the number line. And because they call this thing the fundamental theorem of algebra, it has to be true even for something like this. X squared equals -1. This is where our new number comes in, because there is no square root of -1. There's an answer for +1. Square root of +1 could be positive or -1. Okay, that's a real number. It goes on the real number line, just like our two answers up above us. This is not a real solution. It has no real number, no real solution. But Gauss, our super smart mathematician in the past, said that if we start with something squared, it has to have two solutions. They're just not going to be real numbers that you're used to dealing with. Okay? We can't draw those solutions on a real number line. In fact, the place that we would do this, we could, I don't even want to use this word. I hate using this word. We could imagine the number floating up above the number line, up above at 1 and at -1. It's not on the real number line because it's not a real number. It'd be floating up above, and we call it an imaginary solution. Now, it's a terrible name. A lot of us don't like even using that name because so many people think, oh, we just made it up and it's imaginary. So it doesn't exist. But it does exist. In fact, most people tend to call this a complex number, a complex solution, or just a non-real. So it does. It has two imaginary solutions, two complex solutions, or two non-real solutions is what we would call it. And we call this I for imaginary. So I equals the square root of -1. I'm going to show you a short clip from a YouTube video. I'm also going to include that clip here in our playlist too, so you can watch the whole video from the beginning. But I do want to show it to you here in this video so you get the sense of what it is. They did this really nice job here in this video of explaining how we can see this on a parabola. So they have graphed x squared plus 1. It's a parabola. It goes through +1 on the y-axis. And they've got it turned like this because they're going to find our solutions, because normally solutions to a graph, or roots of a graph, or zeros of a graph happen where they hit the x-axis. But this doesn't hit the x-axis. It has been slid up 1 unit. So here is where its solutions actually happen. They pull our parabola into a third dimension. So our solutions are not just this one parabola that's stuck in 2 dimensions, but it's kind of like you can picture it floating above the page or behind your paper, right? So kind of floating up in space above. Once we see this thing in its whole beautiful glory, now we can find where it crosses that axis. It's just in a different dimension. Okay. And we don't even want to pull it into a third dimension. It's not like an X, Y, and Z, because you can graph X, Y, and Z. If you take college geometry, you'll do those kinds of things. So I don't want to get too far into that because those things might come up. But just know that it does exist. Now we do use I for very real applications. So I can't stress this enough. I cannot see electricity come out of an outlet. I know it's there though, because as soon as I plug a lamp in, the lamp gives me light. And I also know that if I plug in too many things into one outlet, I will break the outlet. I'll blow a fuse or a breaker. And so that means there has to be a limit to how much I can plug into that outlet. And if there's a limit, there has to be some kind of mathy number that helps me find the limit of what I can calculate or count, even though I can't see it. So electricians use I all the time. They use imaginary numbers, complex numbers, non-real numbers. They're always doing this. So do people who work on a big, giant scale of things, like thinking about what happens out in space. Okay? So universes are also growing at this amazing rate, but we can't see our universe grow. We have to use imaginary numbers to make that happen. Okay? So even though we call them imaginary or complex, they do have very real applications. That's a big point that I want to make sure is clear. So on this real number line, if we're going to draw an arrow starting at 0 that represents 3, we would draw this arrow that represents 3. On a number line, an arrow starting at 0 that represents -5, we would do that, and we would draw an arrow here that represents -5. Here, we're going to have a way that we can start to identify I. Okay? So these are very real numbers. We're going to start seeing that we can have these imaginary scale. And because the square root of -1 equals 1i, they put this point up here at a positive 1i. And we can also keep on doing some more other things, like draw an arrow starting at 0 that represents 3 square root of -1, 3 times -1. Well, that's just 3 of these i's. So that is how I would draw that arrow. I would draw it up like this, that has me at 3i. And -1i, I can draw that arrow. It would start here, and it would go down here to -i. So I is the square root of -1. And -5i, -5 i's, starts here and goes down 1, 2, 3, 4, 5, would go right here. That's -5i. So I know it's going to take a little bit of getting used to and figuring out exactly what we can do with this I thing. But there it is. Non-real numbers that are not on the real number line, but they are out there. They are non-real numbers, imaginary numbers, and we'll start seeing what makes them complex in future lessons. All right, go watch the rest of that video in its entirety about that floating parabola. It's pretty cool. It still blows my mind.